Hello, welcome everyone to this TMSI webinar. My name is Pauline Oak and I will be your host for today. In this webinar, we have 3 speakers who I would like to welcome. The first 2 speakers are Donatella Simonetti and Antonio Gogeascoechea. They are PhD candidates at the University of Twente in a group focused on neuromechanical engineering. They will talk about their ongoing research that they're doing in their PhD. And I'm very curious to learn about what they are doing with high-density EMG. Then afterwards, I'm very happy that Jan Peuscher is joining us today. For those who don't know, he is the founder of TMSI, very knowledgeable about high-density EMG, and for that reason, he will be presenting some history of high-density EMG and also talk about our new grids, the Textile HD-EMG grids. Before I give the word to our first speaker, Donatella, I would like to go over some house rules. As you may notice, your microphones are turned off at this moment. So if you have a question during the presentations, please use the Q&A button at the bottom of your screen and ask your questions using that feature. If you would like to save your questions for the end of the presentation, you can also press the button to raise your hand, and then I can unmute you and you can ask your questions. For the questions in the Q&A, placed in the Q&A button, I will go over those at the end of the presentations. Well, then I would like to ask Donatella to please start the first presentations. I hope you will all enjoy this webinar.
Thank you. I will share my screen. Okay. Can you all see my presentation? Okay, thanks. Okay, so hello everyone. I'm Donatella Simonetti. I'm a PhD candidate at the biomechanical department of the University of Twente. And today I'm going to present you our work towards a rapid and advanced musculoskeletal function assessment. But why we're doing so? Usually in clinical environment, the way the musculoskeletal function is assessed is really simplistic. Usually the physician asks the subject to walk on a straight line for 10 meters at a comfortable speed and fastest speed possible. And then just looking at this task, the physician evaluate the functional assessment of the subject. So as we can see, this kind of test is quite rapid, is low cost, doesn't require any instrumentation, but is not accurate at all because it's not based on quantitative information. It's just based on the knowledge and experience of the physician that in that moment is evaluating the subject. On the other hand, in biomechanical assessment, it's possible in biomechanical laboratory, it's possible to use different kind of technologies such as motion tracking system, force plate, electromyography, and musculoskeletal modeling technique. And all this technology can really give quantitative insight on the musculoskeletal function at muscle tendon unit level. So it can really help the clinician to understand what's happening, also internally, the patient. But this kind of assessment is not fast. It's quite lengthy in terms of setup. So placing manually the EMG sensor, find where the muscle belly are, and place markers and other kind of sensor. And also quite costly because all this instrumentation are really expensive, but as we said before, it's quite accurate because can really give quantitative information on muscle forces and joint kinematics and muscle activation. So what will be the best probably is to having a balanced test that can be rapid, but at the same time give quantitative information on the musculoskeletal function. And in the project I'm working on is called Get Under the Skin. We are trying to fill this gap between the functional assessment categories and what is possible in biomechanical laboratories. This project is in collaboration with other companies such as TMSI that is providing the EMG system, Barzo that takes care of the textile part of the technology. And then we have the San Martin Clinic where we can test our technology on impaired subject, in particular on stroke individuals. And the project goal is to transform rehabilitation for stroke patients. We want to achieve a personalized treatment that is based on objective and quantitative data on muscle activation, fourth generation, and that can be obtained in a fast and clinically viable way. But let's see how we want to do this. Our solution, the solution we are proposing is based on 4 main elements. The first one is a wearable technology that can retrieve biomedical data. Then we have EMG clustering and joint kinematics and joint dynamics that can help us to transform the output of the wearable technology in the right input for then our 4th element, the musculoskeletal modeling. And in this way, we can then estimate internal muscle parameter. Now I will go more in detail on each of these elements. And so let's talk about the first element, the wearable technology. The wearable technology is a lower leg garment that consists of 64 electrodes, 64 dry electrodes. And in the future, the idea is also to add IMU sensor, but this is still in progress. The GATS project developed so far 2 prototypes. The first prototype that was developed mainly by TMSI is called the Zero Series prototype. It consists of a commercial compression sock with 64 circular electrodes that were distributed in a grid 8x8 grid. This garment was made just in a single size, and each embedded electrode was connected via an individual cable to a multi-channel desktop amplifier, as we can see in the picture on the right. However, then during the project, a second prototype was developed. This is a more compact prototype. It's called the Beta Series prototype. This garment is made in a way that can be easily put on the leg, around the leg of the subject, and it can be wrapped around and closed just with simple Velcro strap that you can see in the intermediate figure, where are those red lines. It has still 64 embedded electrodes. Those are custom made and screen printed grids that can be easily attached in the inside of the garment with Velcro. This prototype was made in 4 sizes in order to match different lengths and circumferences. And as we can see also, the cable management has been improved because we don't have 64 cable hanging around, but now we have all them. We just have 8 of them, 1 for each column, and they are then linked together and connect to the connector. So this is our first element, the wearable technology. Next element is of our solution is the EMG clustering. So we have 64 electrodes that are unknowingly placed on the leg, but we need to find which electrodes is related to which muscle in order to then extract muscle-specific activation. To do this, we develop a multi-channel clustering that takes the 64 electrode activation during a few gate cycle of a slow walking and extract muscle-specific electrode cluster that can record the activation behavior of specific leg muscle. And then we can use those clusters to compute muscle-specific activation. For the sake of time, I will not go too much in detail in this clustering, but I will invite you to read the paper we published recently, and you can find the QR code on the top right. So I will go now on the third element. So once we have the wearable technology, we were able to process the 64, the information from the 64 electrodes to extract the muscle-specific activation. But in the future idea, there is also the idea to have IMU data, IMU sensor from which we could extract information such as acceleration and quaternions. And then we want to process those data to compute joint angles and reference joint torque. And this step is mainly based on an open source software called OpenSim. So once we process all the output of our wearable technology, we have muscle-specific activation, we have joint angles and reference joint torque. Then we can use those information to drive a musculoskeletal modeling, and so estimate internal parameter of the muscles, such as muscle forces, joint torque, or joint stiffness. And muscle forces, we think, is a really important feature, because it's the most direct estimate of the patient strength. And the availability of this information in clinics could really transform the way a treatment is designed and performed. In the following slide, I will show you a couple of studies where we use this pipeline, except for the IMU data part. We had two studies. A first study was on 8 healthy subjects. These subjects were instrumented with the 0 series prototype on the right leg and 33 reflective markers, and were performing a different task on an instrumented treadmill with double force plate. They performed different tasks such as forward walking at 3 different speeds, backward walking, running, and side step. Then we used the same pipeline, but this time we did our study on chronic stroke individuals that were instrumented with the new prototype, the beta series prototype, were still instrumented with reflective markers and were performing a walking task, 2 walking tasks at different speed on floor-embedded force plate. Now I want to show you the result of our solution, the result in terms of output of DMG clustering and the output of the musculoskeletal modeling. The first result is on the study, on the healthy subject study, is the output of our clustering methodology. And to compare the activation, the output of our clustering pipeline, we manually identified electrodes from the grid that were lying on top of specific muscle bellies. We then compare the average activation across all cycle events for each muscle and each task between manual and automatic activation. Here we show the result for just one subject. The cluster were extracted using just one single task, working on 1 kilometer per hour and using just 3 gate cycle of this working task. And then we used the same cluster to compute muscle specific activation for all performed tasks. And as we can see, this cluster anyway led to electrophysiologically consistent muscle specific EMG envelopes. Then next step was to use both manually and automatically retrieve EMG envelope to drive a musculoskeletal model and then estimate joint torque. In this slide, I'm showing you the result in terms of estimation of ankle torque. The ankle torque estimate usually estimate using manually automatically derived EMG envelope are compared with respect to the inverse dynamics. So the joint, the experimental joint torque that we can compute using reduction forces and joint kinematics. And we can see that the torque estimate with manually automatically derived EMG envelopes display very large similarity. Anyway, there is an underestimation of the plantar flexion peaks, the negative peak torque during walking at the higher speed. And this discrepancy seems to increase with the speed. Now I will show you a preliminary result on stroke individual. So here I'm showing you a couple of videos where you can see one of our subjects that is working on this floor embedded force plate at 2 different speeds, preferred speed and fast speed, as fast as they could. in a safest way. And in the bottom, I'm showing you the comparison between manually and automatically retrieved EMG activation. In blue, we have the manual activation, and in red, the automatic activation. So the output of our EMG clustering. And we can see that we still have a really large similarity between the two envelopes, manually, automatically retrieved. Now I want just to conclude my presentation saying that what we are aiming is to develop a wearable technology that can put together a soft leg garment and also a signal driven pipeline for automatically derive the position of muscle belly within a 64 EMG grid, and also put together a model-based estimation of ankle torque during a set of biomechanical different motor tasks. So we can really aiming to use a fully wearable technology that together with signal-driven pipeline, our clustering and the musculoskeletal modeling can really give us quantitative insight in a rapid way on the musculoskeletal function. And the fully wearable technology can really reduce the setup time. And together with the musculoskeletal to DMG clustering, we don't have to manually understand where the muscle belly are. We don't have to manually place electrode. We just have to wrap around this garment. Then we also develop a clustering that can really give higher repeatability and consistency in the electrode placement with respect to the position of the muscle. And also we show that the automatic retrieve EMG-driven neuromusculoskeletal simulation can be as accurate as using the standard setup, so manual placed electrodes. So the proposal technology, the technology we're proposing has really the potential to prevent the time-consuming muscle manual localization, and it can really facilitate the use of advanced EMG-driven modeling pipelines in clinic, but not only, it can also be used in recreational or occupational domain. So it's really a promising technology that can achieve this rapid and advanced musculoskeletal assessment viable in clinical and not only environment. I want to thank you for your attention. And yeah, if you have any questions, please don't hesitate. I will give now the word to my colleague, Antonio Gogeascoechea. And thank you again for your attention.
Thank you, Donatella. Let me share my screen. And set the timer. Yep. Can you hear me and see me perfectly?
Yes.
Yeah, okay, nice. Hello, everyone. My name is Antonio Gogeascoechea. I'm in the last year of my PhD. And as Pauline said, I work in the same department as Donatella. So although we have different projects, there is certain overlap in our work. In particular regarding the use of high-density electromyography, of course, and also the use of musculoskeletal modeling. However, the goal of my PhD, or the focus, is more on the motor neuron part. So the goal of my PhD is to develop neuromuscular models that can predict how motor neurons respond and adapt to electrical and mechanical stimuli, especially in motor impaired individuals. And this is aiming at a closed loop neuromodulation of spinal motor circuitries. In this presentation, I'm going to talk about how we intend to achieve such a goal by translating motor neuron properties into twitch mechanical properties in vivo. So our motivation is to restore movement in an optimal manner. Neuromuscular injuries such as a spinal cord injury or a stroke disrupt neural function, and this results in multiple repercussions. The ability of interfacing with alpha motor neurons via high-density EMG allows us to understand how human movement is altered with impairment, and also, it allows us to develop neurorehabilitation strategies to restore natural function. However, there are some issues with current spinal modulation techniques, such as transspinal electrical stimulation. And one of them is that most of these techniques are applied in a blinded way. I mean, with hand-tuned parameters and with no direct knowledge, at least, of their effect on motor neuron activity, and therefore no knowledge on how this translates into a mechanical benefit. This in turn limits personalization. And despite the fact that there are some techniques that indirectly infer the effects of spinal modulation, they often rely on additional interventions such as stretch reflex, H reflex, or transcranial magnetic stimulation. And these themselves are external interventions, so they make the probing more complicated and they prevent real-time applications. So what we propose here is a high-resolution framework based on 4 main pillars. First, the use of neurorehabilitation devices such as spinal stimulators and exoskeletons. Second, the employment of high-density electromyography, which allows multiple recordings of electrical activity within the same muscle. Third, to take advantage of these multiple recordings and use blind source separation to retrieve alpha motor neuron information. And finally, neuromusculoskeletal modeling to quantify the impact of such neuromodulation at the mechanical level. The first 3 pillars enable to open a window into motor neuron activity and to be able to modulate their impaired behavior. In our previous work, for example, we looked at how transspinal direct current stimulation changes neural features. In this study, we aim at building causal relations between the neural and the mechanical levels of human movement. State-of-the-art signal-driven musculoskeletal models, such as the one that Donatella was talking about, typically use a heel-type muscle representation with a single contractile element that has a single twitch behavior. However, in a muscle, we have multiple motor units with different recruitment and split properties. And modeling this is the key for linking the neural activity with their mechanical counterpart, which is the innervated muscles themselves. And this link could lead to a closed loop neuromodulation. To test this framework, we used a big repertoire of data from 4 healthy subjects who perform isometric dorsi-plantar flexion contractions at 3 different ankle positions. And the exercises consisted of following reps up to different levels of activation and at also different rates of activation. And a total of 256 channels of monopolar EMG were recorded from the lower leg muscles. And again, this allows to interface directly with the central nervous systems. And we do this through convolutive blind source separation. And from these firing events, we can obtain motor neuron statistical distributions according to their features. Specifically, we are looking at recruitment threshold and discharge rate. And what we want to do here is to translate or to map these neural features into contractile properties. And these contractile properties that we're mapping right now is like time to peak and peak amplitude. And to do so, we first discriminate motor neurons according to their neural features, again, according to recruitment threshold and discharge rate. And here we can already see some overlapping clusters, which may correspond to slow and fast motor neurons. And we compute here a linear combination of these features and we project the data onto this eigenvector. In this figure, we see an histogram of the projected data. And what we do here is we link it with the contractile properties found in humans on clinical studies. Specifically, in this example, it is with the contraction time. To couple these two bimodal distributions, we compute linear piecewise interpolations. And finally, we apply this transformation onto our original distributions. And we obtained like this distribution where we can already assign to each motor unit contraction time in this example, depending on where it falls in this histogram. So I just want to remember that the contraction time is one of our explicit parameters of our model. So once we obtain the twitch properties for each motor unit, we design their specific twitches as an impulse response of a critically damped system. Here we have the peak of the twitch and the contraction time. And well, by doing the convolution of each spike train and their respective activation dynamics, or the respective twitch, sorry, we obtain the motor unit specific activation dynamics. And well, here we employ the activation dynamics that we got here to drive a subject-specific musculoskeletal model. The musculoskeleton kinematics, that is the fiber length and also the moment arms, are computed via a set of V-splines that depend on the ankle angles. And the net torque is computed by multiplying the obtained force here from the heel type muscle model by the moment arms. And finally, we also have a calibration tool to optimize musculoskeletal parameters. Specifically, we are calibrating optimal fiber length, tendon slack length, and maximum isometric force. And we do so by using the experimental torque and comparing it to our predicted torque. So this is, in a nutshell, the entire methodology. Here we have some examples of the torque prediction of our model. Our model is in orange, and the EMG-driven models is in yellow. And in gray, we have the reference torque. A very quick visual inspection shows some improvement, especially in the shape of some ramps of how it tracks them. For instance, in here. And also we can see a good match in the with our models to match the peak amplitude. However, due to decomposition issues, we are not able to decompose lower threshold motor units in high torque trials. This is a trial that goes up to 70% of maximum voluntary contractions, and this goes up to 90. So what happens here is that we decompose fast motor neuron populations, and these overshadow these low ones, that is the first recruited ones. So that's why we have these gaps. We are not decomposing firing events here. And this is an issue that we will address in future work. And here we have a compilation of the normalized error values across all conditions and all subjects. The blue corresponds to our models, and the red ones to the high density EMG-driven model. And although the high density EMG-driven models show slightly lower errors, they are statistically very similar to each other. And I would like to emphasize here that our main goal for now is not to improve the torque prediction with respect to the EMG, but to get deeper insight into motor neuron properties and also onto muscular properties, while still maintaining a similar performance to the EMG models which are our gold standard. Although I would say that in future work, we could for sure improve our errors. And to quickly wrap up, we proposed a framework based on quantifying in vivo neural activity and coupling it with its mechanical counterpart, that is with the twitch properties of the muscle. And our framework showed accurate predictions comparable to the results of the EMG-driven model. And the advantage of our framework is that we gain insight into neuromuscular properties, which can later on be used to infer the effects of neurorehabilitation strategies on both alpha motor neurons and also the innervated muscles. And finally, we believe that this will open up new avenues to better closed loop modulation techniques. Thank you very much for your attention. If you have any questions, I will be happy to take them at the end of the session. And now I think it's turn of Jan.
Okay. Hi, everybody. Well, I was already introduced, and indeed, my name is Jan Peuscher. And I'm the founder of the company. We started actually a long time ago, 30 years almost, the two of us. And we need the next one. Okay. And we were situated, we started in a barn near an old farmhouse. And at the back of this barn, there is a rather large golf course. In the beginning, we were two of us. A few months later, there were 4 people in the barn. And in the winter, we were wearing gloves because otherwise you couldn't hit the keyboard, and you can imagine what happens during the summer. So we moved several times to another building, and at the end, we moved to a building in Oldenzaal, the farm, the Valkenaar, oh, beautiful. This is a multi-company building, so it is not completely ours, but we are in the top stock, half of it. And today we are about 20 people together. So now, of course, you're interested in how we come to grids, multi-electrode measurements, and the development of high-density EMG grid. So the first time that we did some measurements of multi-electrodes was a long time ago, and that was in gynecology. We tried to measure the EMG of the uterus, which is smooth muscle, very, very difficult to measure. But because I worked a long time in gynecology, and I knew that there was a very large question of, can we predict preterm birth by measuring the muscle of the uterus? So we started with a number of electrodes, and that electrodes were stuck in a garment, in some textile, and we did some measurement. And here you can see what you get. First of all, you get a beautiful maternal ECG, and from the maternal ECG, you can calculate the heart rate and heart rate variability. And here you see even the sinus arrhythmia. That means that is the breathing of the mother. And here you see the heart rate of the fetus, which is about 140. Very variable. But we were interested in the EMG, and that is very difficult. Here you see an example, but normally it is hardly possible to measure the EMG of the uterus because it has a frequency band of about 0.05 and 2 or 3 hertz, which means that the variability of the offset, the respiration, the breathing noise and modulation of the offset, the bladder, the gastro, and every muscle that has signals inside the band 0.5 and 3 or 5 hertz is disturbing your measurement. But here, this is one of the most beautiful ones. It comes from Eindhoven. You see that you can see that that there is a continuous signal along a row in the grid, which means that the driving force, the pressure, is going from up to down, and this is the beginning of a delivery. So we did a lot of trials in gynecology, uterine contraction, urology, but we tried to do something on neurology and neuro rehab as well. Then, of course, we tried to make our own array. And these are two examples. This one was made to make our own electrodes, very small electrodes, 2, 4, or 8. And they were used for neonatal care, for sleep analysis, chin EMG, eye movements, etc., etc. And this is the first one that we made to try to make an array of screen-printed electrodes. It was on a plastic sheet. The plastic sheet was not very flexible, which means that if you paste it on a muscle and you do some walking, then the lines that connect the connector with the sensor are cracking, and you lost your signal. So this was a beautiful trial and some in order to gather some technology, but it didn't work very good. So we went on and we had some first attempts to make an array with test pins. In that time, we already had a close cooperation with the group in Nijmegen from Stegeman, who actually are the inventors of the grid. Here you see 2 types of, this one is a real one array, and this one is a double array. This one is made with test pins. No need to use any gel because you stuck them directly through the skin, and they had a beautiful connection to the tissue underneath the skin. No need to tell you that it is not very convenient and not easy to wear, but it worked. One of the examples that we have brought from Nijmegen is a grid, one array of a grid that is placed on a muscle. And you see here near the end plate zone that's in 60% maximum voluntary control, contraction, there is a signal, but it doesn't come to the tendons. It disappears, and that is something that is typical for generalized myotonia. Here is a healthy person, and you see that the signals are traveling along the fibers from the beginning, the end plate zone, to the end of the tendons. So that is one of the applications that could be carried out in clinic. The next one, this is already, again, a grid from Nijmegen, made with test pins. And here you see the beautiful an awful test pin that that directly enters your skin and gives you a beautiful signal, but it hurts, it is not convenient, and actually you shouldn't use that very often or wear it during movement. The next one, that was this one, already was placed on the skin by double adhesive tape using gel. And this was a research in Nijmegen as well. And that was used for muscle cartography, because you wanted to know, this was a research on the force and fatigue and muscles of trumpet players. And actually you wanted to know where is the end plate zone and how is the direction of the fibers. And here you see that the direction of the fibers and the end plate zone is completely different from what you think and what you thought that it might be before you place the electrodes on the skin. So it is rather difficult to imagine, for instance, in mouth and facial muscles, where the end plate zone is and where the fibers are going to. Then I'd like to introduce the new one, the Textile the EMG grids, the high density EMG grids from TMSI today. Here you see that it is a very flexible textile, double-sided adhesive tape, very easy to stick on the muscle, very comfortable to wear, and it is very easy to connect the 32 channels to the connector box, and that connector box is transferring the data to the amplifier. It allows you to study all types of dynamic movements. It reduces a lot of movement artifacts because the flexible grid is following the movement of the muscle underneath the skin. There is no big movement artifact. During jumping, there is no high frequency offset modulation noise, so it is an optimal solution. There is no cracks as we had before in the grid itself. So, and that passed with gel electrode is quite easy, as you will see in a few next sheets. This is the grid. It's flexible textile material. It is suitable for use on muscles that are contracting, and you all know that if a muscle is contracting, it pressures and it will have another position, and it makes a pressure on the paste and on the gel of the electrode, and even the double layer of the sensor is not much influenced by the pressure, so there is almost no movement artifact. The interface between the electrodes is 8.75 millimeters. Of course, it is very little flexible because the grid has to be flexible, but it is more or less stable interface, 32 channels, and it is a pre-applied double-sided adhesive tape is on it. The data is sent to the amplifier by a very thin adapter cable. Here you see how the grid is placed in the connector. It has a spring-loaded connection pin, so the pressure on the connection part is always exactly the same. It gives no movement artifact. Connection is always very very stable, and it is very easy to use and convenient to wear. Then we are coming to the amplifier. The cable is connected to the amplifier with only one connector. The amplifier is, of course, the technology is rather old. It already existed before TMSI started. You can measure in average reference and common reference, but you can make all types of be it multipolar trials, and you can indeed combine it with other types of inputs like pressure, accelerometers, angle, foot switches, whatsoever. The data can be transferred to the computer wireless or with a wired data transfer. So you have all types of possibilities, and you can wear it quite easily on your back. Then we are going to start the video. Just one moment. Let's have a look. There we go. There we go. Okay, the textile is, of course, it's not pre-gelled. You have to gel it, but it's quite easy. You just put the gel inside the holes. The double adhesive tape is, or the other side of the tape is removed. Quite easy to stick it to your skin. And here you see how easy it is to connect the grid to the amplifier. First of all, the impedances of all the electrodes are checked. Then you see whether the sensor has a good connection with the amplifier. And here you see the stable and very beautiful noise-free signal. And that is one of the very nice qualities of the amplifier. You see that the signals are kept in range, so there is a type of reset of the offset. Otherwise, half of them would be outside range, and we like to show you how it is. If you have a look at the range here in front of the trace, you see that the stability of the offset is very, very good, and you hardly see any movement artifact causing an offset change. Afterwards, we can see that you can jump, and in jumping, I expect actually a very large offset change and variety, but you can see it, but it is hardly visible. It means that there is no pressure on the interface of the gel and the electrode, which means that this is one of the most beautiful electrodes to do a dynamic research on EMG. And you can, of course, show the signals in a color map. Then, of course, you should see how the transfer from all the electrodes are running underneath the electrode, underneath the grid. And this is one of the visualizations of this grid. Now we have to change a little bit.
Okay, thank you, Jan.
Okay. Okay.
Very nice presentation.
There you are again.
Also, thank you, Donatella and Antonio. I see that we already have 2 questions in the chat. For anyone else that has a question, please feel free to type it down in the Q&A. Otherwise, please raise your hands and I will unmute you. So we got 2 questions actually from Leo. Thank you, Leo, for being here. First question he has, or statement that he has, is great presentation, Donatella. He asks, how many IMUs would you like to add? And what exactly will they bring in terms of diagnosis?
Okay, thank you for the question. So the idea is to use 4 to 5 IMUs. We need for sure 3 on the instrumented leg where we have the sock, one of the foot, shank, one on the thigh, in order to have also the joint angles for the ankle and the knee, because we are using also biarticular vertical muscles. And then we want for sure another IMUs on the pelvis. And probably we will need also a 5th IMUs on the other foot. So we are going to use 5, and if we can try to go down to 4. And the information that we want to extract from them is, as I said before, is mainly to extract information that can be used for musculoskeletal modeling. So joint kinematics, so joint angles, ankle and knee angles, and joint reference torque, so ankle torque. And those ankle torque are really important in the musculoskeletal modeling, because we need to first calibrate the musculoskeletal parameter, the muscle parameters such as tendon slack length or optimal fiber length. We need to calibrate each muscle parameter with respect to each specific subject. And then we can actually estimate internal muscle forces and joint torque. So the information we want to extract are mainly joint kinematic and joint torque that then are important for the musculoskeletal modeling.
Okay, thank you, Donatella. Then Leo also has a question for Antonio. He says, if I'm not mistaken, all your 256 channels are recorded from the surface. This will give less weight to the deeper motor units, correct? I could imagine that this is not so important in healthy muscles, but maybe more so in pathological cases.
Yeah, thank you. Thank you, Leo. It's actually a great question. You are right. We cannot access, at least with our current methodology, to deeper motor units. And this may have some weight in pathological cases. In future work, we plan, a colleague and I, Rafael Ornelas and me, are trying to merge our work. His work is based on an optimization framework to recreate the artificial motor neurons, the ones that we are not able to reach. So we would like to try to merge our methodologies and see if this would have a greater contribution also, even in healthy muscles, to fill the gaps that I was describing before in high torque trials. Thank you, Leo. Okay,
thank you. Then we got a 3rd question from Louis. He would like to thank all of you for the presentations, and he has a question for Donatella. He asks, did you apply gel on the 2nd version of the garment electrode, or was it fully dry?
So the idea is they are dry electrodes, so we don't want to use any gel, and we didn't use any of it. The only thing we do is just wet a bit the leg with salty water, so just normal water with a couple of spoon of salt. We just make this solution, and then we just wet a bit the leg with this salty water. And actually, we don't even shave the leg. So the idea is to try to have as minimal setup as possible in order to be as rapid as possible.
Okay,
thank you.
Yeah. Does anyone else have a question or would like to raise their hand? Okay, I don't believe there are any questions left. I also see that it's almost an hour gone, so we're exactly on time. Yeah, I would like to, if there are no more questions, please. I would like to thank Donatella, Antonio, and Jan for your effort for this presentation. Thank you very much. I think everyone really liked your presentations. Regarding these new grids, they are now available, and if you have any questions about them, please contact us at info@teamsi.com. So we're already planning our next webinar, which will be on October 11th, so in a month's time, and it will be about our new amplifier Apex. Again, I would also like to thank all of the attendees for being here. And yeah, I hope you all enjoyed. Thank you very much. Okay.
Thank you, Pauline.
Thank you for organizing the webinar.
Have a nice day. Okay.
Bye-bye.
You too. Bye-bye.
Bye.